Fuse current limiter simulation. In this example we will simulate the fuse current limiter. Fuse current limiter consists of porcelain body filled with the sand, two steel plates and conductors. Conducting parts are colored with yellow. The input data is the rated current 100 ampere, and our task is to calculate the temperature distribution. As you can see, the conducting parts cross-section varies, so the first problem we need to simulate is a DC conduction problem. In DC conduction problem we will calculate current density distribution in the conducting parts and the Joule heat losses distribution. Then in steady state heat transfer problem we will use the losses distribution to calculate temperature distribution. Here is the three-dimensional model in a CAD software. This is not QuickField, and you can see there are several bodies here. The sand filling is not included, and I will export all these bodies in the step file. Model. Then I start QuickField, create new problem. This is the allocation folder, and the problem name is DC limiter. Next I choose the problem type, which is DC Conduction, and the model class, which is three-dimensional import. Now here you can see the three-dimensional model editor window, and the only option available here is to import the step file. Here is the file, and I will import it. Okay, now we have 8 bodies in the model, and the simulation workflow is the same as in two-dimensional analysis. We should assign labels to geometric objects. Block labels are used to define material properties, and face labels are used to define boundary conditions. To assign the label to the object, you should first select the object. To select the object, you should click it. So I click here, and the face is selected. To select the body behind this face, I should click the face again. Now you see the body is selected, and I can type in the label name here. Porcelain. And the label appears here in the tree. Next, I would like to assign labels to other bodies, but they are hidden inside. How do we know what is hidden inside this? There are several options. We can hide this body, or I can make it transparent. Right-click the selected body and choose transparent. Now we can see conductors that are placed inside the body. But if you try to click the conductors, you will still select the body. This porcelain body is transparent, but it is still there. So let's hide this body. Again, I first click to select the face, second click to select the body, and in the context menu I choose hide. Now we can manipulate with other objects. Again, I click the face and click again to select the body behind the face. And I can use the control button to select multiple bodies at the same time. These two bodies are covers. I type in the label cover. And again I will hide these bodies. The only object left is a conducting material. In fact, there are several bodies here. To select them all, I will use the rubber band. Right click and drag. Okay, now please note the color of the selection. With the rubber band I have selected bodies, faces, edges and vertices. Everything inside the rubber band is selected. I will assign the label to the bodies only. Copper. Okay, now I will unhide all bodies. Please note that the porcelain body is still transparent. Now I should provide physical properties to the materials. All labels without properties have a question mark. Now electric conductivity of copper is 55 megasiemens per meter. Okay. For other bodies I do not specify any conductivity. Just open and click OK. This way I tell QuickField that we intentionally switched these bodies off. And now you can see the exclamation mark next to the bodies label. We have finished with bodies labels assignment, and now we would need to assign boundary conditions, electric potentials and currents. Right click the copper and choose high all but this. Now let's select the terminal face here. Let's assign label current to this face. Okay. And to the other face I will assign label potential. Double click the label in the tree and type in the potential value here, 1 kilovolts. Double click the current label in the tree and type in the normal current density value, which is current divided by the cross-section area. Well, the current is 100 ampere and the cross-section area, let me check, here it is, this is the cross-section area. So for the current I specify current value amperes divided by the cross-section area, meters squared. That's it. We have finished with labels editing and can proceed with the mesh building. You can build the mesh in 3 stages. Mesh for the edges, then mesh for faces, and then the mesh for volumes. Once the mesh is built, you can run the simulation. Save all simulation files. Well, here you can see the electric potential distribution in the conductors. The potential value is 1 kilovolts, and I can adjust the field picture and switch on the current density distribution. As you can see, the current density distribution is not even. In some parts losses are higher and in other parts losses are lower. To calculate losses in some specific part, I will use the integral tool. Again, I will hide all objects but the copper conductor. And select the fuse. Again, first click to select the face, second click to select the body behind the face. Now in the fuse element you can find the losses, which is about 2 watts. And this value will be used in thermal problem to calculate temperature distribution. In fact, in thermal problem we specify not the total power loss but the power density, which is power divided by the volume. So I'd better start Microsoft Word to store the values there. So this would be, so this is the power loss in the fuse power loss, and I need the volume meter cubed volume. The current distribution looks symmetrical, so I will select both sticker parts. Face selected, body selected, another body selected, and we'll use the average value. So the losses in these parts is this value, sticker watts losses, and the volume is this. And we have the terminals. First click to select the face, second click to select the body, and hold the control button to select multiple objects. Now these values for the terminals. The joule heat value, and the volume. So we have finished with the DC conduction problem. We have calculated the current density distribution and extracted some useful values, the joule losses in specific elements. A quick note before we started the thermal analysis. With integral calculator you can calculate not only the volume integrals but the surface integrals. For example, let's calculate the current value which is passing here, just to make sure that we have specified the current density correctly. I click the face and here is the current value, 100 amperes. You can also use the cut plane to calculate the integral values in the cross section. For example, here is the cross section, I can open this picture in the separate window and calculate the integral value here. Again, the same 100 amperes. Okay, now let's proceed with the thermal analysis.